Here we go. Okay. I absolutely hope that we're live now. We're using a bit of a different setup. It looks like I might be the one streaming for this episode. So that this is going just like a bit more live fire. So just give us a few seconds while we try and figure out if everything's working. Rory, if I could ask you just maybe even just to check on Twitch that this is actually streaming, because I think it is, but I'm not 100% sure. But you'll also need to unmute and tell me if that is the case. Think it's live? Oh wait, this isn't. Okay. Okay. Well then, welcome to what we hope is actually another episode of Solidity Fridays, which may or may not be coming to you live. I am William Schwab, and I'm going to hand it over to Ben to give a full introduction. Okay, it is an intermediate language, which you can almost see on the screen, just because I seem not to be capturing my whole screen right now. But the doc's called an intermediate language, which means that Solidity, as it compiles down, at first it compiles down into something kind of in the middle before it goes all the way down to bytecode. And that thing in the middle is Yul, so it's like an intermediate representation. But yeah, like it looks a lot like opcodes, but instead of just using the actual hex code for each bytecode, which is what bytecode is made out of, that it uses like the names, so it's a bit more human readable. And I believe that there are even a couple of immunities on top of that, if I recall correctly. But yeah. So we figured kind of the best way to get into Yul is to take a look at actually, I mean, you'll see over here, we're in the Solidity docs. Since I seem to have messed up, like, displaying my screen, you can't kind of see, like, the left column or the URL or anything, but this is actually the Solidity documentation. There's a section in additional material called Yul, which unsurprisingly is about Yul. At the bottom of that, there's actually a complete ERC20 example of Yul. Like, this whole thing is Yul's way of representing an ERC20 contract. Now, if you're interested in developing in Yul, I don't know of a way to develop straight and raw Yul like this. Fuel Labs of Sway fame have something called Yelp, which maybe we'll look at something written in Yelp in it if we have time after this. Which is like Yul Plus, you get it, Yelp, yay, which has extensions for Hardhat, I know, and maybe others that allow you to write in kind of their superset of Yul and to code directly in it in files that have a .yelp extension. But as far as like raw Yul goes, I don't know if there's a way to actually develop straight in it. But without further ado, let's just take a look at what's going on here. So you'll see they kind of get an entire ERC20 here into, oh wait, it's longer than I thought it was. I was going to say into not so much code, but it's actually longer than I thought. You will see that it does have a concept of functions over here. So it's kind of like an assembly that's like a bit of a superset on top of on top of just like pure EVM bytecodes. But what you see here is this idea of object is a concept of like having a contract. And then you'll see there's a couple of objects nested inside of it. You have a code object right here, and then you have an object nested in that called runtime with code. So really the first thing that like you kind of need to get to when you're dealing with Yul is, so this first code brick right here, this object, that's the constructor. As in, that's what gets run even before you have an actual runtime of the contract. Then when you get to runtime, this is kind of like the body of the contract, as it were. I'm halfway tempted to actually, like, go deep and pull out the yellow paper, except it would probably take me, or the beige paper. It would probably take me a little bit of time to find that. I'll actually just try and improv it, though I'm probably going to get this a little bit wrong. If there's anybody in comments who figures out what I get wrong with this, like, please do set me straight. As far as contracts go, so when you deploy a contract, the constructor is run, and then also the bytecode of the runtime is stored in some kind of special place in the client. I'm forgetting exactly what it's referred to. And then you've got the storage of the contract for variables. And then also kind of like, the memory and all of that. That's the big difference between a constant or an immutable and a regular storage variable, which is that constants and immutables go into the actual contract's bytecode, as opposed to being stored in storage, which makes them cheaper to read. So that is kind of just like a little very half-baked introduction to what Yul's going to look like. You'll see everything else here is a part of this code object, which should get unbracketed right there. I don't know if you could see that, actually. That might have been off the screen. But yeah, okay, so let's take a look at this for a sec. What's going on in this constructor? So first we have store. So for anyone who's a bit familiar with assembly languages, so basically you have these registers of memory that you can push to, or there's also different forms. But one of the big things that you'll see in things that are dealing with the EVM is where they're storing. So you have two options in general. You can store something in storage, or you can store something in memory. Storing in storage is famously more expensive. But it's persistent. So if it's something that needs to be set, so it has to be set in storage. Whereas if you're just in the middle of using a function, you need an ephemeral variable, so memory is going to do you better a lot of the time. So we're starting at 0, as in this basically is in storage. You have this whole big storage area. So you could start in the middle of storage. You don't have to start writing at the beginnings. Like, let's say you already have stored some variables and you need to store more, you'll want to offset how you're storing. You're going to want to put it like a bit further in. I should actually just open up EVM codes for this. Give me a second. Yes, that's right. I am a proud Firefox user. And okay, here we go. Wow, this is going to get cut off a bit, but okay, here we have, oh man. Okay, give me a second. I'm actually going to try and figure out how to fix this. Give me a sec. No, wait, no. If I do this, and then I do. Okay. I think we're figuring this out. Give me a second. I apologize. Okay, whatever. That's good enough for right now. So here we have store. No, it's not good enough for right now. Lol. Almost getting there. There we go a little bit. Okay, so this is EVM codes, which is evm.codes. That is a top-level domain. And it goes through all of the different EVM codes and kind of, like, shows you what they are. So, as you can see here, there are... Wait, okay, here we go. Stack input. Key 32-byte key in storage. Oh, wait, that might not be what I thought it was. I thought it was an offset. Maybe it's which register, not an offset? Wait a second. No. Okay, I think I made a mistake. I said originally it was an offset. I think it's actually which slot the values are going into, and they're all divided by slot. So this is the key to which slot in storage you're putting the data into. And then the second argument is what value is getting stored. So if now we go back to this, so we're storing in slot 0, and what we're storing is caller. Caller, as I recall, I believe is message.sender, but it's worth taking a shot. It's worth checking just to make sure. Get caller address. Yeah. So this is what we generally refer to as message.sender in Solidity. So we're storing message.sender in 0. I don't recall why. It could be that this is kind of like an ownable thing, and we need to know that. But in any event, that's what we're doing. So then we deploy the contract. How do we deploy the contract? So first we copy the data. I'll have to check that also. Get me some data copy here. Data copy. Okay, so this is storing it into memory. So the first thing over here is actually 0, which is where in the memory we're starting from. Data offset and data time. So data size. Data offset tells us how far into memory we're going to write. And no, that's not right, is it? Byte offset in the call data. Oh, in the call data. Okay, right. Stop me if I'm rambling too much over here, but we need to know how far into the call data to read. So what we do is we read the entire runtime, and that's how far in. That's its way of saying it's kind of like the dot length over here. Since we're reading the runtime object, this says basically just read the entire object. We also need to know how far into memory we're going to need to write to allocate the memory for it. So we also say whatever the size of runtime is, that's how much that from 0 to there is where we need to allocate. And then we return it, which is how you deploy the contract. As in we return from 0 in the memory to data size runtime in the memory. So basically we return the entire runtime, and that is how we deploy it. So far, so good. How am I doing, Ben? Yeah, I'm not sure. I'm not sure. I wonder if it's something that you have to do. I mean, we were thinking of also taking a look at week 11 if we have time. Yeah, they don't bother. Yeah. Oh, and mint in the Yule. Oh, they have a mint there, so it might actually need to be a. Oh wait, it's not on the screen. Whoops, thought it was. For mint. Yeah, Dakota's address. It looks like it. No, wait, no. It just looks like it can hop in though. Oh, here. Yeah, the lower one. The lower one requires it, but not that one. It looks like because it's calling the internal function mint, and then then it requires called by owner. I see what you're saying. Yeah. Wow, they judiciously use internal functions here. I haven't seen that done too much, probably because most people who are using Yule are trying to kind of obsessively gas optimize, and they don't want the extra jumps, I'm assuming. Give me 1 second just to give myself a little bit more of the screen here. I'm actually just gonna and a little bit more, I think. I'll try to do that. Let's try and that should be a little bit better, I think. Wait a second. What have I done? Sorry for the technical difficulties over here. Okay, so yeah, now let's take a look at the runtime. So the runtime is kind of like the body of the contract. So first, it looks like there are no payable functions. As in, any time that you're not putting payable on a function, essentially you have to do this. You have to require that the call value is 0. Call value is message.value. So what you're doing here, just kind of like work out message value being 0 is required. And like you're adding that logic in anytime you're not putting payable down. It took me a while, I think, to understand this, but taking a look at some of the gas optimizers, it really does strike me that some of them, I would say especially Transmissions 11, big shout out right there, as they got deeper into actual how like EVM opcodes work, it was kind of a matter of syncing up like your logic, the logic that you're writing with the assembly that it's going to be broken down into. So I know a lot of them have beef that Solidity actually makes you have to write payable because essentially you're opting into more code. You have to opt out to minimize the code. By not writing payable, you're getting extra code put in because now it has to put in this require a zero call value on every function, even though, so to speak, you didn't ask for it. I know we were Ben. We were talking about the kind of rage against the custom errors thing. That also is like really assembly based. I think it was T11s. I can't remember who wasn't so happy about the custom errors in Solidity 8, and it also had to do with just the way things are represented in in the assembly. He held it was like another place where like the logic of the way that you think about things and the solidity that you're writing differs from the way it's going to show up in the assembly. Like one's going in one direction and the other's going in the other, if that makes any sense. I think that kind of was just random English words in a sentence, but I hope it made sense to somebody. Let's wait and see if we get into Week 11, because I'm assuming there should be more errors to talk about. There's hardly any here. And I think it'll get a little bit easier if we actually have a jump eye in front of us. So now, actually, this is what your contract kind of like looks like under the hood, by the way. This is what we call a jump table, which should be familiar to anyone who's coded anything other than like basic JavaScript. Well, I mean, JavaScript does have switches too, but yeah. Okay, so switch selector. So here's what a selector is. What's the best way to get into this? So there's actually a very nice article on the Linum Labs blog. I am not only shilling this because I am a Linum Labs alum myself, but another Linum Labs alum, Veronica Kutz, who now works by Optimism, so you get that she obviously knows what she's talking about, wrote a very nice article on function signatures and function selectors, which actually, for me, is usually one of the top hits whenever I try searching for stuff on, using a search engine, looking for a function selector. Basically, just bear with me for a thought experiment for a bit. You've got a function, let's say transfer. So your standard transfer in an ERC20 token, it takes one argument address, which is where you're sending the tokens to, and another one uint256 amount, which is the amount of tokens to the full decimals that you're sending. What would happen if you would take the name of the so like function transfer parentheses address comma uint256 and parentheses, no spaces in the parentheses. Actually, I bet there's something here. Let me use a catch-jack. And then you catch-jack it. Yeah, okay, I think we got this. Input, so we can do this. Trans. Oh, except that you can't see anything on my screen. How do I do this? Oh, what's going on here? Give me a second. Here we go. Okay. Transfer. It needs function in it, doesn't it? I'm pretty sure it does. I can spell. Function transfer address uint 256. Except I wrote 245. Brilliant. Okay. So this over here is called the function signature. It's a catch-jack 256 of the function, the name, and the arguments packed in like this without any spaces. Okay, great. So what? So, yeah. Oh, it's just transfer? Okay, thanks for checking that. Okay, so actually, this is the function signature. Thanks for looking that up. Now, the reason why this is relevant is actually, is that 4 bytes? I can't remember. I might be missing a letter or two. The way that, no, I needed more than 3, 6, 8. I needed 8. Okay. The way that, is that right? I think that should be right. Yeah, there we go. Whoa, wacky it. those mess with each other? Weird. Okay, yeah, sorry for that. But in any event, the way that the EVM kind of refers to your function isn't by its name. It's by taking the first 4 bytes of that catch-ack. So over here, A9059CB. And it uses that to refer to it. Like to the EVM, this is what transfer looks like. Yeah? So that's called the function selector. That's kind of how the EVM selects your function. And so over here we've got switch selector, as in assuming that a function call is being made. You're calling the contract runtime now. As in this contract is deployed, it's an ERC20 token. Let's say you want to transfer. So when you transfer, you're going to be using that 0xa9059 blah, blah, blah as the function selector. That's what, Ethers or Web3.js or whatever you're using is going to be breaking it down to under the hood or in your hand-selected bytecode written, encoded transaction that you're submitting through your own local node that you run over radio waves. So what's going to happen is it's going to hit a jump table. Basically, it's going to say, okay, let's take a look at this function selector that you've just passed in. All right, is it this? No. Is it that? Is it this? Oh, there we go, 0xa9059CBB. So it's like, okay, so now I'm going to run this code over here. Now, here in the Yul, they're using a lot of internal functions. But basically what happens is now this code gets run, and it returns even at the end of it, and then you're back out. So basically what you've got here is all the cases are all of the different functions that exist in this contract. And then a default that reverts if it doesn't recognize any of these. Now, the default can also be your fallback function, just so you know. That's what a fallback looks like in Yul. It's gone through everything and it doesn't find any of the function selectors, but there's still something it can run over there. Okay, so now let's take a look. Over here, it looks like they've made internal return functions, which is funky. So we've returned uint, and it returns an internal the result of an internal function called balance of, which decodes whatever is coming in as argument 0 as address. I'm assuming that's what that 0 is, but we'll have to see. They use an internal for total supply. I kind of wish they would have put the actual logic and the functions here. Like, I feel like it's a bit, wonky to have to keep on scrolling down. But I guess they wanted to display, the use of internal functions in Yul. Over here for transfer, so it runs an internal function called transfer. Transfer from, approve, allowance, and mint. You'll notice that, at least as far as I'm aware, there's no actual differentiation here between being a view function and not being a view function. I think that has to get handled by the compiler before it's down into Yul. I don't think that Yul itself differentiates. Okay, so now we have the internals. So we have mint. Mint takes an address and it takes an amount. Over here, notice that you don't specify a data type. There's a require of called by owner. I'm debating if require is something that they did, or if that's actually native to Yul. I don't remember right now. I'm just taking a quick look. Yeah, it is. It is something they made. Usually you just have to do an if yourself and then revert it. And that's kind of what a require looks like. But they kind of handmade their own requires over here. So this is almost like, I kind of feel like this is something halfway in between Yul and Solidity, But in any event, require called by owner. So basically what that means is they're calling their called by owner function, checking if the address that's calling the function, if caller, is going to be the same as what's stored in storage slot 0. Because we know that's where owner is, right? So where is that called by owner? Here we are. Here we go kind of down into some assembly equations. It's going to return this CBO over here, and it assigns, that's the assignment thing, the walrus operator, as I've heard it called. It's going to store a bool if owner and caller are equal. Owner was a function above which just reads the address that's stored in slot 0. It checks if they're equal, and it returns the bool that happens as a result of that. So when you require called by owner over here, basically you're just requiring that the address in storage slot 0, wherever I was, is equal to the color. Okay. So then we have yet another internal function. Man, this is driving me nuts. Amount, which adds to balance. Also, I guess mint tokens is to up the total supply, and this one is to actually increment the balance. And then it emits a event called transfer. I don't remember how Yul handles events. I actually kind of want to see that. I don't remember that off the top of my head. Okay, fine. Note, by the way, no semicolons anywhere over here. We have transfer, which again is going to an internal function. Surprise, surprise. Approve, revert of 0 address, set allowance, emit approval, fine. Transfer from. First needs to decrease the allowance because, oh. I think there's a bug in this. Is this a bug, Ben? I think there's a bug. What happens if someone calls transfer from and they transfer from themselves? It's going to depend what that decrease allowance by function is, but if they don't check there who's sending, then it's going to like get wonky. It's not too bad. What's going to happen is it's going to probably underflow a person's allowance for themselves, which I guess isn't the end of the world, but it's like an extra right also. There's a check there. Decrease allowance. Let offset require less than equals. So then it's just going to revert. As in, it'll revert. Let's say I want to transfer you tokens and I call transfer from. And I put in my address. No, but let's say I call transfer from. Like, unless there's some condition here. No, there isn't a condition. Then it'll revert. Because my allowance towards myself, we would assume, would be 0. And it'll underflow, which then will get checked and it'll revert down there. I'd personally call that a bug, but it's not the end of the world. It doesn't lead to loss of funds or anything, but I mean, a lot of platforms, I believe, even kind of default to transfer from as opposed to transfer, especially since a lot of the template contracts, transfer just calls transfer from. So you save yourself an extra jump if you put your address into transfer from first. And then in transfer from, they just, they say basically either allowance or that it's you. And if it's not you, then you decrement the allowance, not otherwise. Whereas here, like the owner of the tokens themselves can't actually call transfer from unless they approve themselves. You'll notice that a lot of the checks that are here, or a lot of the functions that are here do not have checks that are in, say, like the Open Zeppelin library or something like that. Second. What was I going to say? Wait, what's going on here? Sorry, while I try and figure out what's going on with my screen a bit. As in, the approves aren't checking. Open Zeppelin, I don't think lets you approve yourself even. But yeah, whatever. That's a bit of a side thing. All right, so now we have execute transfer, which is kind of what gets called in transfer and in transfer from. Takes a from to an amount. It reverts if it's sending to the 0 address, which might even be in the ERC20 standard. I don't remember. Deducts from balance, adds to balance, and emits transfer. It is interesting that they put that in, though. I don't know. Is it that bad if someone transfers to the 0 address? Beats me. In any event, call data decoding function. So we have selector over here. I made a little bit of a mistake by selector, I see. I thought that was native Yul. That is also not native Yul. That is them assigning a value to S, which is what gets returned by the function, which takes the call data, loading from 0 to some large number. What's going on here and why are they dividing it? What is going on here? What happens normally when you get there? So normally you just take the first 4 bytes of call data, which makes sense. That's all you need. But instead, what are they doing here? I don't get what's going on in this line. It's loading call data 0. Dividing it. I'm assuming this is a way of slicing the first 4 bytes, but I have to admit I'm not exactly sure why. I guess 4 bytes times this equals the full size of the call data. I'm not sure why they wouldn't just slice it. Yeah, like why not slice? Yeah, I'm pretty sure it is. M slice right there. Could be this is cheaper. I mean, I could also just check by going slice. Oh, wait. Oh, did he make up M slice? He might have made that up. No, that's it. Must be a, I wonder if it's a Yelp thing. That might be a Yelp thing. It could be that there isn't here. But there should be... I mean, there should be a way to load just the first 4 bytes, I would think. Not sure, though. All right. Leave that as an open question, maybe. So now they have these, like, make sure something's an address, make sure something's a uint. So first, for an address, it decodes as a uint. The offset is where it's supposed to start reading from. And then if is 0, and v not. Whoa. Okay. So this is not... Whoa. What's going on here? V is not... No, and means that has to be true and that... I don't get what and is doing here. What is and doing here? So, oh, okay, we're doing with the manipulation. Okay, I'm assuming this is a checksum being implemented here. I don't know enough about checksumming to say one way or the other, but I'm assuming that if something is properly checksummed, this should come out as not 0. And then, therefore, if it is 0, it reverts. That would be my big guess over here. But I don't know. And to get to there, they have to use decode as uint, which has this thing v. Here we actually have, I think the first time we're seeing variable assignment. You can create a variable here. So you let position assign a bit operation over here. And again, I don't know exactly what we're checking here. Maybe if it's big enough or too big to fit into a uint. I'm not sure. And then v becomes the call data from position. Okay, returning a uint basically stores a value v in memory and then returns it, because that's where returning returns from memory, so you have to make sure it's there. Return true just returns 1 as a uint. Is that really? I wonder if that's really... Oh, because it's only going to store 1 there. Yeah, okay. All right. Then we get into events. So we talked about function signatures before. Actually, let me just give it a bit more space here. We talked about signatures before from functions. So events also have similar signatures. So over here, they're just coding in the signature hash for transfer, the signature hash for approval. and then they'll emit it out. They have their own emit event that isn't native Yul also. What they do over here is they put in the hash. Oh, it's interesting. They always just assume that the first two arguments are indexed and then they have a non-indexed. Okay, fine. They store the non-indexed in memory and then log 3. So that's going to push 4 values on. First is going to come 3 values. First, this looks like the offset for the hash. I'm assuming that's right. Or is that the data? Wait a second, what's going on here? Append log record with 3 topics. Okay, so byte offset memory, byte size to copy, and then 3 topics. So yeah, I'm assuming the 0 and the 20 here are for the non-indexed. No, that doesn't make sense, does it? As in, indexed arguments and events always go to topics. The first topic, topic 0, is always the signature. Then it assumes, I guess, that the next 2 topics are these indexed arguments, and I'm assuming the rest are being returned in memory in those 20 bytes. I'm probably not nailing it 100% right, but it's probably something in that general direction. And we have some storage stuff. We kind of took a look at this before. Total supply is loading at a total supply position, which it keeps track of over here. As in, it uses slot 1 for the total supply, and it just always just loads that out of storage and returns it. Yeah, I'm tempted to kind of jump over here, some utility functions over here also. I'm tempted to jump over here just so we have a bit of a chance to look at Weath 11. What do you say? Okay. Okay, cool. So Weath 11 was written by David Mihal, who's ironically probably famous for coming up with that Ethereum fees site, but has done quite a bit more. So what do we have over here? We have his shot at adapting WETH or wrapped ether in being straight in Yul. So this is an ERC20 token, but it has a lot more going on in it also, which is pretty cool. So like seeing some kind of advanced Yul usage over here, I think this is like a really good way to go. Let me try and expand my screen a bit. Is this readable? That's probably a little bit better now. Give me a second. Why? There we go. All right. There we go. All right. Wait a second. Sorry for all my technical kind of like lulls over here. Okay, so what do we have over here? We've got object Weath 11. That's the contract name. Then we're in the constructor over here. So already we're getting some comments. Push this on the stack before data copy to prevent memory overwrite. So, okay, there is permits over here, which is why we're seeing domain separator and all of this stuff. It feeds in chain ID, which is actually an available opcode, and calculates domain separator off the bat, and sets that in initial domain separator. Okay. I don't know if native Yul has consts, by the way. I think native Yul might only have lets. I think this might be a Yulp thing, but I could be wrong about that. Okay, now after we have the domain separator, we're ready to do some data copying for the runtime. So we saw that in the Yul also. Start at position 0. Read the entire runtime and write the entire runtime. All right, we're setting some immutables here. So that has to be done in constructor, of course. there's something called initial chain ID, which we'll put chain ID into, which looks like, incidentally, that they're going to use a trick that I saw in Soulmate originally, I think, but this should predate it, because I'm pretty sure this predates Soulmate entirely, which is you store what the original chain ID at the time of deployment is, and anytime someone calls domain separator, you make sure that the chain ID is still the chain ID, and if it is, then you use the immutable. Otherwise, you calculate it again from scratch. That helps you if they're in the case of a chain split. Now, I mean, I kind of feel like this is esoterica because, like, I mean, we haven't really seen a major chain split since Ethereum Classic, to the best of my own personal knowledge. Feel free to correct me if there has been a more recent incident of something like that. But at the same time, I know it and it's cool, so I'll just flex it whenever I get the chance because, you know, what's knowing esoteric stuff like Yul if you don't get to flex with it every now and then? I know it's not even a Yul thing. That's like a permit thing, but whatever. Set an and then you set already an immutable what the initial domain separator is so that you can read that much cheaper if there hasn't been a chain split. Okay, great. And then we return the contract. The runtime of the contract, that is. Okay, great. Oh, so you already need to write this function. That's interesting. Since you're using this function in the constructor, you actually have to put it in the constructor also. So you can see the hard-coded catch-ack of the domain, EIP712 domain over there. You can see a catch-ack of the name, catch-ack of the version. I guess it doesn't need a catch-ack of the symbol. Been a while since I've checked. And it needs the chain ID, and it needs the address of the contract. Oh, you can figure out the address already. That's cool. Okay. And then it catch-acks all that. Runtime. Alright. So const call data. Leave first 432 byte chunks for hashing, returns, etc. As in, we're saving 4 words, 432 byte words, and we're only starting call data after that. That's interesting. Not sure I understand why we're doing that yet. And then I'm almost sure this is a Yelp thing. There's an enum for balance, allowance, and nonce. Okay. If call data size is 0, so then you know already that you're going for the fallback. So require that the call value is more than 0 because you know that they're depositing because it's like, you know, yeah. And what it's allowing you to do is it's allowing you to just send ether to the contract. And I'm assuming it'll just send you WETH back, but I guess we'll see over here. Because now you're hitting the fallback. There's no call data. The only thing that's coming in is call value. You figure out the caller's balance slot. Wow, cool. So what you're doing here is basically you're finding the depositor's WETH balance just by reading their balance straight out of the slot. As in, okay, so that's what this enum is doing. It's storing where balances are, I'm assuming. Or not exactly where balances are, if I remember right. I'm trying to remember exactly the way mappings work. It's something like you take kind of a signature of the mapping, like maybe the name and data types or something like that. I don't remember exactly, and you hash that. And then maybe you also hash the value of the key. So it's not like sequential, if I remember right. I think it might also have to do with hashing the value of the key. But I don't remember. So, yeah. I feel kind of stupid giving my half-baked guesses over here, but that's what you're stuck with. So, yeah. Then you take the balance of the depositor, and you add the... Wait, where did we get WAD here? Have we defined a WAD? I'm assuming this is the amount that's being deposited. It's just interesting to me. I don't know where it came from. Huh. balance of destination, the balance of destination. S load caller balance slot, S store caller balance slot. No. I'm a bit stumped on this line. Oh, there's a comment. I'm a real genius. It's a comment. Desperately attempting to prove my complete inability to read code live. Okay, so balance of destination. We load up the caller balance slot into that. So we're loading it into that variable. Then we store at the destination, like where the caller's balance is, their old balance plus call value. Okay, there we go. Oh my gosh, wow. That was, I think, the most embarrassing thing I've ever managed to do on this stream. Okay. Memory, store, call value. Okay, so then we stored the call values, and that's the offset in memory again. So we're just writing from the beginning of memory, we're writing in the call value. And then it logs the event raw, as in from 0 to 32. This is interesting. Topic event transfer. I'm wondering if topic is just a way of hashing. Does that make sense? I feel like in the EVM it's actually SHA-3 as the name of the opcode. Huh. Wonder why this is valid. Wonder if that's also a Yulp thing. Don't know. In any event, then 0, then caller. 0 for, I mean, you can even see the source. Because it's getting minted, they're minting WETH, and they're sending it to the destination. And that's the amount that they're sending. And then stop, which I suspect is either Yulp or a handwritten function. It's cool. It's cool that he did this, just because it also means that you don't have to go through the jump table. Because obviously the fallback is going to be the last thing you hit in the jump table. So it is kind of cool that this happens. I guess it means that you have an extra jump every time you call the contract. But jumps are pretty cheap. Like, no one's counting jumps. I mean, if your function isn't at the top of the switch table anyway, you're jumping. Huh. Okay, so if you're not calling the fallback, so then it basically copies all of the call data to memory. It slices the first 4 bytes of the call data, and now we hit the cases. Yeah, so it's interesting. There seem to be extra hashing functions here. Like sig seems to be a way of taking only the selector. Because, I mean, basically what it'll do is it'll hash everything here in quotations and then just slice off the first 4 bytes, I'm assuming. Now, that does make this much, much more readable, which is also interesting to me. So, like, instead of having kind of the raw 4 bytes that we had over here in Yul, over here in Yulp, we're able to actually kind of see what's going on in the source code. We've only got like 1 minute left, and I'm realizing I don't even think we're going to see a jump I over here. So just to kind of quickly pay that debt off, talking about modern custom errors in Solidity 8 versus the old reverts. Basically, jump I means jump if. As in, there will be some kind of condition, and only if the condition is fulfilled do you jump. So what a revert does is very simple. You have a condition, like let's use the one that we were looking at in the Yul code, which is if the owner is message.sender, is the caller. So what'll happen is you'll have jump I that the caller and the owner are the same. And that'll jump over one opcode, and the next opcode will be revert. So if the owner is equal to the sender, then you jump over the revert, otherwise you hit it. That would be the way you would classically make a revert compile down into Yul. Now, the thing is, with the custom errors, you actually end up kind of doing the opposite. Basically, what you're writing into your code is if if message.sender not equal to owner, then revert with like not owner. And what that does in the code is you're going to end up with two ifs. First, you're going to have this if. Then you're going to have, give me a second. If that, then, gosh, my brain's locking up. But you have the first if, which is the if that's actually written into your code. So if caller is equal to owner, then if you pass through that, you jump I on true. Oh, right. Yeah, wait, you should have it nested, right? You should have a jump I with an if nested inside of it. But what happens essentially is you're only jumping if the condition is the opposite of what you think. I think I'm totally messing this up actually. Oh man, I feel bad. I burnt the omelet on that one. But yeah, something like that. I hope somebody out there is able to make sense out of what I just said, because I know that I am not able to. So at the very least, if you can't figure out what I'm saying, because neither can I hope it at least entertains you. And I think that's going to be a wrap for us. So I hope this was useful for someone out there. I kind of feel like I went on a giant rambling kind of like mess stream of consciousness dumpster fire for quite a lot of this. But I hope that this helps people out there who are interested in getting into Yul and getting into all of these great Gaffs optimizer conversations, even though Transmissions 11 seems to regret everything that he's done with that. But that's okay, Anon. Enjoy. It's good for you. Having a good understanding of Yul, I think, makes you a better Solidity coder also. And then after that, you can check out Viper, where they're all sitting there and snickering about how inefficient it is at compiling in a gas optimized way. And yeah. Any parting thoughts, Ben? Cool. All right. Till next time.